This video is going to look at the questions relating to section 6.3, 6.4 and 6.8 from Walding. So the first set of questions begins, just scrolling through the Kepler stuff, at question 16. So first question here reads, the average radius of the orbit of Uranus is 2.87, blah blah blah. Use the average value for r cubed over t squared from table 6.3 to calculate the period of Uranus in seconds and in years. Alright, so let's go up to table 6.3. So we want an average value here. Now, if we have a look through that last column there, we can see they've used meters cubed and seconds squared, so it's already in the right units we need. We've got Mercury, Venus, Earth, Mars, Jupiter and Saturn. We do need to take an average, so the first things first, we're just going to add them up and divide it by 6 from the count of it. So let's work out the average first, and it looks like a couple of the other questions use this number as well, so that'll be useful for us. 3.68 plus 3.35 plus 3.31 plus 3.35 plus 3.36 plus 3.38, and those will all be times 10 to the power of 18, and we're going to divide that by 6. Now let's grab just a calculator. Now sometimes it can be useful in things like this just to see, well, could we do all the sum of these numbers first, then divide by 6, and then just slap this times 10 to the 18 on the end and see if we get the same number, or do we have to add all them up, multiply by 10 to the 18, and then divide it by 6? Can be a useful habit just to get into checking to see if you can save yourself some time down the track with mathematics. So I'm going to add up the actual numbers first. 3.35 plus 3.31 plus 3.35 plus 3.36 plus 3.38, and that gives me 20.43 times 10 to the 18 over 6. I'm just going to double check that because we're going to use this number a bit. 3.35, 3.31, 3.35 again, 0.36, 8. Yep, great. If I divide that by 6, I get 3.405 times 10 to the 18, and if we look at that list of numbers, we can see the 3.4 is just a little bit above all these ones, which is what we'd expect from this one here, dragging the average up a little bit. Let's try that the other way. 20.43 times 10 to the power of 18, and then divide that by 6. Yep, we get the same number, so always good to check. So our average, we've got r cubed over t squared. Now the symbol we use for an average is just a line over the top of it. In this case it equals 3.405 times 10 to the 18. So any other planet or any other orbiting satellite around the Sun should have an r cubed over t squared of about that. Okay, so we want to find Uranus. We know that the radius of Uranus is about equal to 2.87 times 10 to the 12. We know that the r cubed over t squared ratio should equal our average, so let's set that up. R cubed of Uranus over t squared of Uranus equals the 3.405 times 10 to the 18. Alright. So then if we rearrange this, we're going to get that RU cubed over 3.405 times 10, sorry, not 110, just 10 to the 18 equals period squared of Uranus, and let's substitute that, so 2.87 times 10 to the 12 all cubed divided by 3.405 times 10 to the 18 equals our period squared. So I'm going to work out this and then square root it to get rid of that square, and we'll be good to go. 2.87 times 10 to the power of 12. I want to cube that. So 2.364 times 10 to the 37, and we're going to divide that by 3.405 times 10 to the power of 8. To be careful with dividing by positive power here. Now, the bit on the top was 2.364 times 10 to 37 over 3.405 times 10 to the 8. Now that's 10 to the 37 divided by 10 to the power of 8. That means that should reduce in power, so we should have around 10 to the 29, not 10 to the power of 45, because if you put this into the calculator wrong, then you're going to do this big number divided by that and then multiply by that, which means the power will go up. 2 divided by 3 is just going to be is sub 1, so it wouldn't go to 29, it should go down to 28. And by my calculations, that gives me 6.9 times 10 to the 28, which is equal to t squared. But we need to square root that, obviously. So we get that t is equal to 2.6 times 10 to the 14 in seconds. Don't forget your SI units. This second part of the question, though, wants me to work it out in years. Alright, how many seconds are in a year? So let's first off convert it to minutes. Divided by 60 for how many minutes? How many hours? Divided by 60 for how many hours? How many days? Divided by 24. And I assume they mean Earth years in this case. I don't think they mean Uranus years, because the average value for the rate for the orbit, the period of Uranus in Uranus years would be 1, because that's a period. Divided by 365 gives us a number of, so if we divide by 60, divide by 60, divide by 24, divide by 365 equals 8,300,000. Oh, that seems way too high. 8 million years to do a revolution. No, I've done something wrong. There's no way it's that high. 2.6 times 10 to the power of 14 seconds. Divide that by 60. Gives you that many minutes. Divided by 60. Gives me that many hours. Divided by 24. Gives me that many days, which is like 3 billion days. Divided by 365. No, that can't be right. What have we done wrong there? Let's look up what the actual answer should be. Where's my thing? Physics, textbook, Walding. Chapter 6, and we're looking for question 16. 2.64 times 10 to the 9 seconds. Okay, so there's something I've done very wrong in that first bit, but 83.5 years, which at least is the first number is correct. I'm just a few orders of magnitude off. Okay, so let's see, what have we done here? Radius of Uranus from the question, yes. Average of the thing, yes. R cubed over t squared. That 12 should give us 37, so yes, that looks fine. Have I done my rearrangement wrong? I see what I've done wrong. I have missed an 18 here, so that now had a major power off. So instead of being 6.9 times 10 to the 28, it should have been 6.9 times 10 to the 18. There we go. So 6.9 times 10 to the power 18. Let's square root that number. Gives us 4, 5, 6, 7, 8, 9. Good. 2.6 times 10 to the 9 seconds, which is matching a thing. Alright, now we can do that. Divide by 60, divide by 60, divide by 24, divide by 365. Gives me 83.3 years. Or Earth years. Alright, that's why that check step is always really important, guys. You don't want to have a stupidly huge answer and just go, oh yeah, it must be right because that's what the calculator said it was doing. Make sure that you are considering the reasonableness. I mean, 8 million years for an outer planet to go around, that seems suspiciously high. I'm not saying that they won't be long numbers at times, but you've still got to consider some of the reasonableness, and sometimes those things can be pretty tricky to do. However, our next question would clue us into the fact that this would have been wrong. So our next one is Neptune. Neptune takes 164.8 years to orbit the Sun. Obviously, it's a bit further out than Uranus because it's the 8th planet, so there's no way it takes 164 years if Uranus takes 8.3 million years. So yeah, that was a problem. Use the average value of r cubed over t squared, so that's good, we've got that, to find the average radius of its orbit. So r3 over t squared that we have before, though, that's in seconds. So we're going to need to convert Neptune's orbit to seconds, or Neptune's period of orbit to seconds, and then we can work out the radius of it in meters. So let's see, we've got t equals 164.8 years. Let's multiply that by 365 for days, 24 for hours, 60 for minutes, 60 for seconds. Okay, it's exactly the opposite of what we did up here before. 164.8 times 365 times 24 times 60 times 60 gives me 5.2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 seconds, which is, as we can see, similar magnitude, just double the number, so that's okay. And we had 3.405 times 10 to the 18. So 3.405 times 10 to the 18 was our ratio. Okay, we know that r cubed over t squared equals, let's just call that k for the moment. So r cubed is going to equal k times period squared. R cubed equals 3.405 times 10 to the 18 times 5.2 times 10 to the 9, all squared. Let's do that. Square that number times 3.405 times 10 to the power of 18. We get that r cubed equals 9.2 times 10 to the 37. Now remember, if your calculator does not have a cubic root button, this one I have in front of me does, so yours I really don't think should have much of a problem. Remember, you can raise it to the power of 1/3, 9.2 times 10 to the 37 to the power of 1/3, in which case then you can just use your to the any power, and then what's the word I'm looking for, and then from that put in a cubic root. Where am I? Cubic root, and we get equals 4.5 times 10 to the 12 meters, which if we looked at Uranus before was 2.87 times 10 to the 12, so again similar magnitude, just a bit bigger, so that seems to be fairly reasonable. Okay, our last question here is about that hypothetical planet by the name of Vulcan that I mentioned in class. So let's have a look at that there. It says, there was once thought a planet existed between Mercury and the Sun. What would its period have been if it was a mean radius of 40 million kilometres from the Sun? So let's start that off. 18. We have mention of a radius here equals 40 million kilometres. So 1, 2, 3, 5, 6. So that's in kilometres. Equals 40, 1, 2, 3, 1, 2, 3, 1, 2, 3 metres equals, let's see, count that out, 3, 6, 9, 10. 4 times 10 to the 10 metres, just to make it a bit easier for ourselves. We are trying to work out t, and let's use that same k as before, 3.405 times 10 to the power of 18. That was it, yeah. So, we know that r cubed over t squared, not to subs 2, equals k. Let's rearrange that, so t squared is going to equal r cubed over k equals 4 times 10 to the 10 cubed divided by 3.405 times 10 to the 18. 10 to the 10, that's going to be power 30, power 31. We're going to drop it down by 18, so we should have around 13-ish, and we would have 12 divided by 3.41, so it should be maybe around 17 or 18 in total. Sorry, no, 12 or 13 in total. I'd expect a power around there. 4 times 10 to the power of 10, and we want to cube that. Now we're going to divide that by 3.405 times 10 to the power of 18, and that equals, as I suspected, 1.88 times 10 to the 13, and we want to take the square root of that. We get that t equals 4, let's see, 1, 2, 3, 4, 5, 6, so 4, 3, 3, 5, 4, 2, 2 seconds. Let's turn that into years. Let's figure out what that actually is in a reasonable unit. So divide that by 60, divide that by 60, divide that by 24, divide that, oops, so multiply by 24 then, divide that by 24, divide that by 365. That gives us equals 0.137 years. Again, not really great in terms of what that is. So I'm going to multiply that by 365, sorry, get it back into days, or that equals 50.2 days. So a little bit over a month and a half. So that's that's now reasonable for us to wrap our heads around. So that's half a term pretty much. Okay, those are all the Kepler law questions. Let's head on down to question 19 now. So we're into gravitation now. Calculate the force between the Sun and the Earth, assuming they are about 1.5 times 10 to the 8 kilometers apart. Very similar to what we did this in class, I do believe. However, let's just solve that out quickly. So we have that the mass of the Sun equals 2 times 10 to the 30. We have the mass of the Earth equals 5.98 times 10 to the 24. And we have a radius, or distance between, of 1.5 times 10 to the 8. The textbook uses d. I'm sort of used to using r. It really doesn't matter which way it's talking about, a distance between the two. So we know the force of gravity equals big G m1 m2 over distance squared, or r squared. That's a constant. We've got those other numbers, so we can substitute here 6.67 times 10 to the negative 11 times 2 times 10 to the 30 times 5.98 times 10 to the 24 all divided by 1.5 times 10 to the 8 squared. Okay. 2 times 10 to the 30 times 5.98 times 10 to the 24 times 6.67 times 10 to the power of negative 11. So let's see, 54 take away 11 would give us 43, and that gives us 44. Good, so that's on track. Divided by 1.5 times 10 to the power of 8, square that, gives us a force of attraction between the two of 3.5 6 times 10 to the power of 28 newtons. It is a force, we're still using newtons. Okay, pretty straightforward. Okay, question 20. A lot of context on this question, but it really just comes down to the same thing. Black holes are supermassive collapsed stars. Closest to anything is called the event horizon. Calculate the force acting on a 15-ton spacecraft, so that T stands for ton. Remember, a ton is 1,000 kilograms. At the event horizon of 30 kilometers from a black hole that has a mass equal to 10 times that of the sun. Okay, so a lot of just extra sentencing in there about trying to set up these numbers. We're still just dealing with force of gravity or force of attraction between two masses. Let's identify the value. So mass 1, let's make mass 1 the spaceship. We see it's 15 tons equals 15 tons equals 15,000 kilograms. Mass 2, 10 times that of the sun. So, it's also got 1 ton equals 1,000 kilograms at the end of the question, so that's good. 10 times that of the sun, which is 2 times 10 to the 30, so that's going to equal 2 times 10 to the 31. And we're just slapping another 10 on there. We've got the event horizon at 30 kilometers away, so radius equals 30 kilometers equals 30,000. Now, numbers are there, it's exactly the same as the question before. Force equals G m1 m2 over r squared equals 6.67 times 10 to the negative 11 times 15,000 times 2 times 10 to the 31 divided by 30,000 squared. Okay, 2 times 10 to the power of 31 times 15,000, sorry, times 6.67 times 10 to the power of negative 11. Okay, so let's see, 21, 1, 2, 3, 4, so that would give us 34, 34 take away 11 should be around 24, 23, and I get 25. Oh yeah, that 1, 2, 3, 4, 35. Yep, got that, so that's okay. And then we're going to divide that by 30,000 squared. We end up with 2.2 times 10 to the 16. Now, I'm going, but that's a black hole. Black holes are meant to, like suck light into them. The event horizon is where light couldn't escape, but if we look at the numbers in consideration, yeah, we do have something that's 10 times bigger than the sun, so that increased that power by 1 point, and which might go, yeah, so you change the number by 1, big whoop, but that is saying it's 10 times bigger. It's this number here, the fact that it's only 15 tons, even though this number is a lot closer compared to this number is a lot smaller. You've got 10 to the power of 24 compared to 10 to the power of 4. That's really a lot different there, so that's why that's happened. Okay, that was the last question of that, and we'll be doing the circular stuff, which will cover the next couple of chapter questions. So I'm going to scroll down to the 6.8 questions on gravity field. So question 29. What is the gravitational field strength at a point whose distance from the Earth's surface is equal to 3 radii? Okay, so if we think about gravitational field, so let's use G for gravitational field. G equals big G, the mass of the thing we care about, or the planet, or whatever that's orbiting, divided by the radius squared. Okay. It's the same as this previous formula up here, but we're getting rid of one mass term, basically. So we've got the mass of the Earth. The mass of the Earth is equal to 6 times 10 to the power 24. Let's use that better one, sorry, 5.98 times 10 to the 24. So mass equals 5.98 times 10 to the power 24. It's the radius we care about. Now, excuse me, the radius question here says that it's equal to 3 Earth radii. There's a table just above table 6.4 that says acceleration due to gravity is 9.8 at distance from Earth's surface, which is 0, or distance from Earth's centre, which is 6,400 kilometres. So we're just going to use that as our radius here for our Earth kilometres, 6.4 times 10 to the 6 metres. Note the heading's in kilometres, so if you need to use it in metres, because we are still in SI units, equals 6.4 times 10 to the 6 metres. But we want 3 Earth radii. So let's chuck a times 3 on the end of that. We've got what we need, we can substitute now. So G is going to equal 6.67 times 10 to the negative 11 times 5.98 times 10 to the power 24, and that's divided by 6.4 times 10 to the 6 times 3. Just slap some brackets in there to make sure that I am dividing it by 3 lots of it, not doing a times 3 on the end. 5.98 times 10 to the power 24. I'm going to divide that by 6.4 times 10 to the power 6 times 3. Let's see, times 6 times the power 3 will give us 10 to the 7. 24 take away 7 gives 17, which matches what I've got here. Great. Times 6.67 times 10 to the power of negative 11 gives us, seems suspiciously high. That's giving us a value of 20 million. That seems way too high. Oh, I forgot to square it. The whole thing needs to be squared. That was silly of me. 5.98 times 10 to the power of 24 divided by 6.4 times 10 to the power 6 times 3. Square that. Times, yeah, that seems like a much better number. 6.67 times 10 to the power negative 11. Yeah, there we go. G equals 1.08 meters per second squared. It is an acceleration, so make sure we're using the right unit for acceleration. We can see there that when you are 3 times, or compared to being at the surface of the Earth, you're 2 more Earths up. Now you've reduced it by almost tenfold, so we're down to quite a weak gravity there. If you have a look at the table that's up above it, there's a distance from Earth's centre of 19,990, which is a little bit more than 12,800. 18,000, 19,200. Yeah, so it's just a little bit above 3 lots of the Earth's radius, which put it at 1 meter per second squared, and this is 1.08, so again that matches the numbers up above. Question 30. At what altitude above the Earth's surface must you go for the gravitational field strength to be 1/16th the value on Earth? So what we're looking for here is a G that equals 9.8 divided by 16. 8 divided by 16 gives us 0.6125, and we need to find R. we know mass, that's still 5.98 times 10 to the 24, and our formula G equals capital G m over r squared. If we rearrange this, we'll get that r squared will equal G m over little g. Let's substitute. R squared equals 6.67 times 10 to the negative 11 times 5.98 times 10 to the power of 24 divided by 0.6125. So we should be expecting to have a pretty big distance here. 5.98 times 10 to the power of 24 divided by 0.6125 times 6.67 times 10 to the power of negative 11. Take the square root of that. Actually, just write that in. R squared equals 6.5 times 10 to the 14. Square root that. R is going to equal 22.5 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters. Okay, so like 25 million meters away, or 25,000 kilometers away from the surface of the Earth. Okay. Now, the next question here is not so much a calculator one, however, it does ask us to do some plotting. So, we've been asked here to plot G versus distance from the Earth's centre. Now, when you're doing something like G versus distance, the thing that is before the versus comes on the y-axis, so G is going to be on the y-axis, and distance from the Earth's centre is going to be in the x-axis. So the table there is up in 6.4, so we're going to use those numbers. Now, that first one of G versus D, if we have G here and D here, we get a set of numbers that kind of look like that. Now, if you see this sort of shape, because the next thing it says to do is to comment on the relationship. So this is an inverse relationship, at least. Could be inverse squared. But it's at least inverse. And if you think about it from looking at the equation, well, that seems to make sense, because if we look at this equation here, I use R, but D could be quite a thing. If D gets bigger, G gets smaller. If D gets bigger, G gets smaller. So it seems to be matching it. The second part of the question, though, asks you to plot a second graph to prove your prediction that it is an inverse or an inverse squared. So if you would go and take the D values, so I did 4 graphs. I did D squared, or G versus D squared. I did G versus 1 over D, and I did G versus 1 over D squared. Now, G versus D squared kind of looks very much the same, just stretched out more, which again tells you, yeah, it's still got to be inverse, so that's not really going to help us too much. G versus 1 over D looks like this, which almost looks straight, but if you plot a linear trend line, it does have above and below, and we really get an r squared of 0.9831 from that. R squared equals 0.9831 G 1 over D, which is pretty close. I'm not saying it's not, but it's always worthwhile checking out to see if you get slightly better. And not to mention, the formula tells us it should be 1 over D squared, so always better to confirm. If we plot G versus 1 over D squared, G 1 over D squared, we get a perfect straight line for our points there, and we do get an r squared equals 1, which It tells us it's the perfect match, which is what we kind of would expect anyway, especially for synthesized data. Alright, those are the questions that relate to what we've covered so far in class. I hope they've helped you with your working solutions. Remember to keep on top of things, otherwise they will fall behind. Thanks guys, have a good night.